In the last few videos of Linux for DevOps series, we explored networking, storage, mounts, and LVM. Now it's time to go deeper and understand what actually makes container possible. Containers don't start with Docker, they start with Linux kernel. Have you ever wondered how two containers both can have a process with a PID 1 or a different host names? That's not a Docker magic, that's a Linux namespaces. Namespaces decides what a process can see, while C groups decide how much it can use. In this video, we will focus on Linux namespaces and understand them step by step and only focus on a real Linux commands. So what a namespace really is? A namespace is a boundary. It allows a process to see only a part of a system. The host still sees everything, but the process inside the namespace does not. So instead of just talking about this, let's prove it using the terminal. So let's go back to our terminal. First, let's see the current process list from the host. So for that, we can use a ps command. So ps, it stands for the process stated. It shows all the running processes. Then I'm going to use an option that is -e. That means it shows every process, and -f. So it gives us a full story about each process. So this command shows all the processes in full detail. After that, I'm going to use a pipe symbol. The pipe takes output from one command and passes it as an input to the another command. So here I'm going to use another command that is head. So head only shows the first 10 lines of output by default. If I press enter, it shows all the processes but only the first few lines of it. So as you can see, it shows all the running processes on the system, and this is the host view of it. So the first column, that is a UID, that means a user ID. It tells us which user owns this process. So as you can see, most of the processes are owned by the root user only. Then we have a PID, that is process ID. So every running process in Linux gets a unique process ID. So here you can see that is 1, 2, 6, 7. These are the process ID. And the PID 1 is the first user space process always. Then we have a PPID, that is a parent process ID. That means this shows who started this process. As you can see, the PID 1 is having 0 as a PPID. That means that started by the kernel itself. But if we have a number here like 2, that means this particular process is started with PID 2. Then we have a CPU usage. This is an old CPU usage field, and today it's mostly informational and often 0. Then we have a S time, that is start time. This tells us when the process has been started. And then we have a TTY, that is a terminal. And here if you see the question mark, that means this process is not attached to any terminal. And after that we have a time. That is, this is the total CPU time used by the process since it started. And then at last we have a command. This shows what program is actually running this particular process. Now we will create a new PID namespace and start a shell inside it. So for that we can use a unshare command. So if I run unshare -pid -fork and -mount -proc and bash. So let me explain this command very quickly. So unshare creates a new namespace, and I'm giving an option that is PID. So -pid creates a new PID namespace. And then I'm using a -fork. That means it starts a child process inside it. And at last I'm using the -mount -proc. That means it mount a new /proc for current process ID visibility. And here if you see the bash, that means it start a shell inside the namespace. So let me press enter here. So the new process ID namespace got created. Let's verify it. So now we are inside the namespace. Right now there is no obvious visual change here. So let's prove we are inside the PID namespace. So let me run echo $. So as we can see, it shows 1. That means we are inside the PID 1. And if I run ps-ef here, so notice something very important here. So we are inside this namespace and my shell is PID 1. So $$ shows the PID of the current shell, that is 1. And if I run the ps-ef, we are only having a 2 process running here. First is the bash, which we just created using the unshare command, and we are inside that namespace only. The PID 1 is special in Linux. It is a first process and it becomes responsible for signal handling, child process cleanup, and process lifecycle. And this is exactly what happens inside the container. Every container has its own PID 1. Just like we created our own namespace, similarly container has its own namespace with a PID 1. Now let's exit the namespace and return to the host. Let me enter exit. So you can think of a namespace as a container. Basically, the PID namespace isolate process visibility. So basically inside a container, processes can only see other processes in the same namespaces. But container doesn't feel isolated. They also feel like separate machines. That sense of utility comes from the UTS namespace. So before running any command, let's understand what UTS mean. So UTS stands for Unix Time Sharing System. In simple terms, the UTS namespace controls system identity. That includes the host name and the domain name. Normally, a Linux machine has its own one host name, but container need to feel like a separate machine. And the UTS namespace allows that. So it gets a new host name to the container. So let's get back to our terminal. First, let's check the host name on this particular system. So let me run hostname command. So the hostname is master01. So this is the hostname of the actual machine. Now let's create a new UTS namespace and start a shell inside it. So for that we can use a same command, that is unshare. So before that, let me clear out the screen. So now let's create a new UTS namespace and start a shell inside it. For that I'm going to use unshare command --uts and bash. So let's press enter. So --uts flag isolates the host name and the domain name for this particular shell. So right now I'm inside the UTS namespace, and if I run echo $, but this particular is still showing the process ID of the host machine. Why? Because we are not inside the PID namespace. So PID1 is still the system D. So the process visibility is unchanged. So even though we use unshare, the PID view did not change. That's because I only created a UTS namespace. UTS control the system identity, that is host name and the domain name. And it does not isolate the processes just like a PID namespace. And that's why we are seeing the different PID here that is coming from the host only. So let's change the hostname inside this namespace. So for that I'm going to use hostname DevOps -container. So let's verify it very quickly. So the hostname got changed inside this namespace, but this particular hostname has been changed only inside this namespace. So if I exit and verify the host identity, so let's come out of it and run the hostname command again. And so this proves something important here. The UTS namespace does not change the host identity. It only gives the container its own system identity. This is why container looks like a separate machines, even though they run on the same host. So the UTS namespace gives container their own identity, not an isolation. So isolation still comes from the PID namespace, mount and the network namespaces. But identity comes from the UTS namespace. So far we have seen PID namespace that isolate processes, UTS namespace that isolates identity. Next, let's look at how container gets their own file system view using the mount namespace. So mount namespace controls what file system a process can see. So let's create a mount namespace in this particular system. Let me clear out the screen first. Unshare -mount and the bash. So this command creates a mount namespace. Let's press enter. So we are inside this namespace. Let's create a directory and mount a temporary file system. Create a directory using the mkdir /temp/namespace -demo. So the directory got created. Let's mount it. Mount -t tempfs and the directory name. So this command mounts a temporary in-memory file system at a specific directory. So the mount attaches the file system to a directory in a Linux. In Linux, disk and file system does not exist on their own. They become visible only when they are mounted. And the -t, it specifies the file system type, that is tempfs. So tempfs means temporary file system stored in the RAM. And the second tempfs is just a file system source name. For tempfs, there is no real device like /dev/sda, so we use the name that is tempf. Think of it as a label, not a disk here. And at last, we are giving a mount point, the directory where this file system appears. So anything written inside this namespace -demo directory goes into the memory, not the disk. Because we are inside the mount namespace, this file system is only visible inside this namespace only. So let's press enter. And if I run mount grep name, so we can see the mount exists here. So here we can see a normal disk mount from the host and the tempfs mount that exists only inside this mount namespace. Now let's come out of this mount namespace. So if I enter exit, so I'm not inside the mount namespace now. If I run the same command again, just to verify, so it's gone from the host. This is exactly how container gets their own file system view. Mount namespace allow containers to mount and unmount file system without affecting the host. So the tempfs gives us a fast in-memory file system and the mount namespace keeps it isolated. So now we have isolated processes, identity and the file system. But the networking also works in the same way. First, let's check the existing network namespace in this. So if I run IP netns list. So if you notice here, there are already multiple network namespaces on this system. These namespaces were not created manually by me. They were created automatically by the container networking layer. If you see the CNI hyphen prefix, that stands for the container network interface. So every container or pod gets its own network namespace and the CNI creates and manages them automatically. And the ID is just a kernel internal identifier for that network namespace. So now let's create our own new network namespace. For that we can use IP netns add and the DevOps -ns. So it will create a one manually created namespace. So let's press enter. So the namespace got created. If I run the same command again, that is netns list. So if you see, the new network namespace with a name called DevOps -ns got created. Now if we want to inspect interfaces inside this namespace, we can run an exec command. So if I run IP netns exec DevOps -ns and the IP addr command, and if I press enter, so it only shows the loopback interface only. By default, a network namespace has no access to the host network. This is why containers start with no network connectivity until CNI wires them up. And if you have worked with Docker or the Podman, this is the same syntax we have used over there as well. Like exec command is being used to go inside the container and run any command on the container. So now let's clean up this namespace. For that we can use IP netns delete DevOps -ns. So it will delete the network namespace. So if I run the IP netns list command again, so the namespace got deleted. I want to tell you one more key point here. Namespaces are not Docker feature. Docker just automate what Linux already does. So all this isolation clearly exists somewhere. Linux must be tracking it internally. So let's see where the kernel stores namespace information. So basically Linux exposes namespace information through the /proc file system. So let's inspect the namespace links for the current shell. So for that let's run ls-l and the /proc/$$ns. Let me press enter here. So each entry here represents a namespace. If the process shares a namespace, these value will be identical. So this shows all the namespaces the current shell belongs to. $$ is a PID of the current shell. That's why I use $, because if you remember, I use echo $$ to get the PID of the current shell. So this is the same thing I used here. So if you see, each entry is a symbolic link to a namespace object inside the kernel. If two processes have the same number here, they are still in the same namespace. If the number differ, they are isolated. And each of these control a different dimension of the isolation. If we see the PID, this number is kernel generated namespace ID. It has no meaning by itself. It's only useful for the comparison purpose. And if you see PID for children or time for children, so these control what namespaces child processes inherit. So when a container starts a container, it puts the container process into a new namespace object, which is exactly what we are seeing here. This is how Linux tracks isolation internally. Now let's compare this with the PID1. If I run the same command, but the number 1, that is a PID1. So here I am only looking at the namespaces of the PID1, the init process of the host. On this system, the PID1 is the system D. Earlier we checked the proc for the current namespace, but this time we are checking with the PID1 namespace. If you notice here, the UTF namespace ID are different. Earlier it was 106 and in the PID1 it's 838. Different ID means different namespaces. So PID1 and my shell are not sharing the same UTS name. That means my shell has a different system identity than the host. So all other namespaces are the same because I didn't isolate them. Namespaces are independent. You only get isolation for what you explicitly create. So that means in the same way container also work because they run the PID1 inside a different set of namespace ID. What you saw today is how Linux kernel creates isolation using namespaces. Docker doesn't create this isolation. It simply uses what already exists in the Linux kernel. Once you understand the namespaces, containers stop feeling magical and start becoming predictable. But isolation alone is not enough. Containers also need network boundaries. In the next video, we will explore how Linux firewall rules control and protect network traffic. If you found this helpful, hit like, share it with your friends and subscribe for more content like this. Thanks for watching. I will see you in the next one.